Hello, this is question 12 from the step 3 paper in 2022. We got the point A lies on the circumference of a circle, radius A, centre O. Point B is chosen at random on the circumference so that the angle AOB has a uniform distribution, 0 to 2 pi. Okay, find the expected length of the chord. So we're back on expected lengths again, which has been a popular topic in the paper this particular year. So let's get a bit of a sketch. So we've got a circle, centre O, we got a point on the circumference A, and that is at a radius A, and we got another point B which is moving around the circumference and it's making an angle AOB, which is going from 0 to 2 pi. So we're moving B all the way round from A all the way around the circumference back to where it starts again, and we have to get the expected length of the chord. Okay, the expected length of the chord AB. So let's get a statement of the length of that chord then. So the length of AB is going to be, well, we can split this into two right angled triangles. So it's going to be two lots of A sine theta over 2. And then our probability function that we're going to have then for the angle, so we're going to have the f of theta is going to be 1 over 2 pi, as in if we integrate that from 0 to 2 pi, we're going to get 1. So working out our expected value of the length of AB, we're going to have to integrate from 0 to 2 pi of the thing we're trying to get an expected value of, and then the likelihood of having a particular angle, which is our d theta over 2 pi. So just have to integrate all of this. We've got an a and a pi we can take outside, and the 2's are going to cancel. So I've got the a over pi integral 0 to 2 pi of sine theta over 2 d theta. So a over pi, then we're going to have a minus 2 cos theta over 2 pi to 0. So let's take the minus 2 outside, minus 2a over pi, and then I'm going to have a cos of pi, which is minus 1, and then take off a cos of 0, okay, which is another minus 1. So I'm going to end up with 4a over pi. Right, that was a nice way to get started. Right, new sheet. So 4a over pi, I'm going to write that on here just in case I need it, and while it's there, probably won't because we're moving on to a part 2, but you never know. Right, the point C is chosen at random in the interior of a circle of radius A, centre O. Okay, so we're now moving from the circumference to the interior. The probability that it lies in any given region is proportional to the area of the region. Random variable R is defined as the distance from between C and O. Right, find the probability density function of R. Right, so we've now got a circle, we got O, we've got some point C, which could be anywhere inside the circle. We've got this distance here from C to O is R. Oh, and of course, we've still got our radius A. So we want the probability density function of R. Right, so if we're varying some radius R between 0 and A, we want our probability density function, so of our capital R, which is going to be a function of this little r that we're varying. We need to figure out what that is. So what is the probability then that our position C at radius capital R is inside our little r radius as we're varying that from 0 to A? So what is that probability? And they told us that it's proportional to the area of the region. So if we've got a region which is extended out to little r, we've got a pi little r squared over the total area, which is a pi r squared, pi a squared, I should say. So we've got an r squared over a squared. So that's our probability. Essentially, that's integrating our probability density function from 0 up to r is giving us that. So if we want to get back to our probability density function, we need to differentiate this, and we're going to get 2r over a squared, which is our probability density function. Okay, right, obtain a formula in terms of a, capital R, and t for the length of a chord through C that makes an acute angle T with OC. Right, so we've now got, so A, R and T, the chord through C that makes an acute angle T with OC. Right, so let's zoom in a bit on this. So we've got our C, we've got our O, so that's C, that's O. We've got a chord now going through C. This is our OC. So we put a chord through C. We've now got that acute angle T. Okay, and this is our chord. So we need a formula for the length of that chord. Okay, that seems not so bad. So we've got then that, well, let's switch over to blue because I'm going to want more lines here. It looks to me as though we're going to want to put this on a, like a double right angled triangle. So if we drop down that height again, then we can Pythagoras this. We've got an A there. We've got a, well, so we can get a capital R is going to give us the height. So if we've got an R sine theta, so we've got two triangles which are looking like this. We've got an A there, and then this side is going to be an R sine, well, T in this case. And then we just need to work out this side using Pythagoras. So we're going to have two lots of the square root of a squared minus r squared sine squared t. Okay, so obtain the formula length of the chord through C. So okay, this equals the length of chord. Length of chord. Right, now what do they want? Show that as C varies with T fixed, the expected length LT of such chords is given by this. Okay, so we're doing expected value again. So this is sort of similar to what we've just done. So this time, so what we do, we're keeping T fixed. So we're varying our position of C. We're keeping T fixed, so it's R that's moving around. So we're going to want to integrate then from 0 to A, because we're changing our R position of the thing that we want to know. So that's what we just worked out, this length of the, well, it'll now be a small r, say, length of the chord. And then we've got the probability that we've got our r value at a particular location. So that's what we worked out in the first part of the question. So we're going to have a 2r over a squared and then dr. So this is our, oh, I should have put an L or T at the start, but anyway, this is what we're calculating here. L as a function of t. So yeah, we just need to work out what this integral is going to be. Right, this is all a bit of a mess, isn't it? I mean, look at it all. Well, I suppose most of these things are constants, really, aren't we? We've just got an r squared inside that square root. So that's going to drop out not so badly. So let's take some stuff onto the outside anyway, because, well, that 2r is going to be useful, because when we differentiate the thing inside the square root, we'll get a 2r come out. So that's just going to sort of go away, isn't it, when we do the integration. So I'll just take a 2 over a squared onto the outside. So that's going to leave me with the bit in the square root. Let's leave some space there. That will go up a power to 3 over 2. Limits in. So I'm going to have to get rid of the 3 over 2, a minus sign, and a sine squared t. So I'm going to have what, minus 2 over 3 sine squared t. Okay. So yeah, it's just plugging in now these limits. So let's take minus 4 over 3a squared sine squared t. And then I'm going to have an a squared minus a squared sine squared t to the power of 3 over 2. And then I've got to take off and well, that's just going to be an a squared rooted and cubed, so an a cubed in all of that. Right, and how have they put it in the answer? Right, they've switched things over to coses on all of this. Right, so we've got a minus 4 over 3a squared sine squared t. Then in the bracket, I've got an a cubed times a cos squared t to the 3 over 2 minus an a cubed. Okay, so deal with the a cubes, and I can turn the minus sign around inside the bracket. So let's get rid of that minus sign there. And so I've got a 4a over 3 sine squared t, so that looks good. And then I've got a 1 minus cos cubed t, which also looks good. So is that exactly what they wanted? Yes, it is. Right, good, I'm happy with that. Show further that L of t equals that. So is this just doing trig manipulation on this? It might be, but I'm going to have to get a new sheet up in order to start looking at this. So yeah, I mean, a lot of it is the same. So obviously I've got the 4a over 3 is exactly the same. It's just dealing with the rest of it. So I mean, I wonder what. Let's get a closer look, I think, at the half sec squared, just to make sure I know what's going on with that. So if I've got 1 over 2 cos squared t over 2. So what is that going to be equal to? So cos t, let's just get these split out. So if I was doing my double angle on that, that's going to be cos squared t over 2 minus sine squared t over 2. So which is going to be 2 cos squared t over 2 minus 1. So if I've got this thing, so cos squared, 2 cos squared t over 2 is cos t minus 1. So that thing is identical to 1 over 1 plus cos t. Right, so I've certainly got that. And I'm wanting to change around quite a lot of stuff here. I mean, it's all coses, so I'm clearly going to want to change that. So I'm wanting to do, so let's say let c equal cos t. Then it just saves a bit of space, doesn't it? So if we've got 1 minus cos cubed over 1 minus cos squared, that's going to be, well, the way they've split it out, looks like I'm just doing a straight, let's factorise that. So 1 minus cos will then go to cos squared. I'd have to have a 1, and I'd have to have a plus cos. And then this is difference of 2 squares. 1 plus c, 1 minus c. So I can get rid of those. So that certainly helps. And then, so they've got one of them. Oh, I've got the 1 over 1 plus cos t going on there, haven't I? So that is going to be 1 over 1 plus cos plus cos plus 1 over cos plus 1. Oh, wow, excellent. So that has dropped out really quite nicely. So, which is 1 over, right, I need to write that out differently now, don't I? 2 cos squared t over 2. So C is just for cos 2. Plus, so I've got that bit already. And then I've got plus that cancels with that, plus c. Okay, so what am I left with all in all? So I've got that 4a over 3, 1 minus cos cubed t over sine squared t is equal to all of this, 4a over 3 cos t plus a half of sec squared t over 2. Right, okay, that was not so bad figuring out that bit. Part 3. Random variable t uniformly distributed 0 to pi over 2. Find the expected value. God, we're on the expected values again of LT. Right, okay, well, we've got what LT is. I mean, clearly we're going to be, they must have got us to put it in this format for a reason. I'd be surprised if not. So we're back on this again, and we're doing So the expected value then of L of t, we're going from 0 to pi over 2. Well, didn't they say it had to be an acute angle t? Makes an acute angle t. I don't know, does that matter? That we're including 0 and we're including pi over 2? So we're including, yeah, we're including values that we've explicitly said on in the thing that we've just worked out. Although, I mean, it is included, isn't it? I mean, it's bothering me with that bit. Taylor formula of A, R, and T. I mean, that was our, Does it matter that we've got, I mean, they're all causes and sines. It's not like we're getting any kind of weird asymptote or anything turning up. What did I work out as the length of the chord is fine if we add t is 0. I mean, if t is 0, we've just got ourselves a diameter. If t is 90 degrees, then it shrinks down to nothing. So there's not anything that really makes any difference here, is there? I mean, I don't think it affects necessarily the answer. It's just that they've specifically told us that it's acute, and now they've included a right angle and a straight line. But anyway, I'm going to push on because I'm not really too sure what else to do about it. If you've got any thoughts on that, then let me know. So we're wanting to integrate this anyway. 4a over 3 cos t plus half sec squared t over 2. And then, so yeah, we're uniformly distributing from 0 to pi over 2. So we're going to have our dt divided by pi over 2. Okay, so what can we do with all of this? That 2 is going to give us an 8. So I'm going to have an 8a over 3 pi. And then I'll have a sine t. And then, well, this is tan, isn't it? It's one of our standard results, a half sec squared. So that's going to be tan of t over 2, going from 0 to pi over 2. Right, so that's 8a over 3 pi. So we'll get, for these, for sine pi over 2, we'll get 1. For tan of pi over 4, we'll get 1. And then we'll take off a 0 and a 0. So we're going to get 16a over 3 pi. Okay, right, so I think that's all right. It's just a slight, why have they told us here these acute angles and then included the straight line and the 0? But I don't think it messes anything up. I think everything that we've done includes that. So yeah, I mean, that wasn't a bad question really, that one. It was a lot easier from my point of view anyway than question 11, which I thought was really, really unpleasant. This one, providing, because we providing you know how to calculate these expected functions, and I mean, the probability density functions are quite easy to put together. And we just did the same thing 3 times really in this. So I would have said this one was easier than question 11. But the stats questions, as I said in the last video, are not really my favourites. But this one wasn't too bad. But I don't think I would have picked it anyway. I mean, most people seem to avoid the ones at the end. I think most people end up doing the all the pure questions. People are on average happier with those than they are with the other ones. But if you're into your stats, this was probably a gift to you. But it's just that a lot of people aren't. But anyway, that's finished off the step 3 paper anyway, which has taken a while, but got there in the end.